Morning. All right, we can start. People drive slow. I'm a slow driver. Slowing down in life. I hate when people are late. Sorry, no, you weren't late. I'm just saying. People that drive fast, they're late. But I think.
Yeah, I was trying to get over it, like getting late.
People who get up early and are on time, they're not in a hurry. Anyway. Who knows? There's a lot of people out there, I know that. That's probably the problem. All right, number 7, free body diagram, right? Smooth frictionless wall. So there's no friction here. I've already removed the wall, right? And I've removed the ground. So your free body diagram, you want to take the supports away. The supports in this case are a pin at the bottom at A, right? Everybody agree? Pin at the bottom. And a wall. So remove them, both of them. Label all the points. Put all the dimensions on. If there's loads, known or unknown, label those. Everything. Point C, point A, point B, unknown theta. So you can put a line in for horizontal, but don't make it look like the ground because we want the ground gone. Okay, how many reactions go in for a pin? Anyone remember? 2. 2. 2 for a pin, X and Y. So what I do is I just put them in without the arrows. And I label them AY, AX, that's our convention. And for a smooth wall, what was the wall doing to the ladder? It was holding it up. Yep, it was pushing on it. So the wall goes in like this, and it was pushing on it. I am going to put that arrow in because it had to be pushing that way to hold the ladder in place. I'll label it BX. Since it's smooth and frictionless, there is no Y force. If there was friction, then we would include a Y force. But it said smooth and frictionless. It gave me the length of 16 feet. So I have that on the drawing. So you want to extract everything out of the word problem and get it onto the free body diagram. Okay. Assuming the weight of the ladder is acting at its center of gravity, sketch the diagram. So really it should have in a weight acting down, the weight of the ladder at the halfway point. So the weight of objects always goes in at the geometric center. This W is some other weight because it's not at the center. It's 10 feet up of a 16-foot ladder. So that was actually pretty complicated because you had to extract information out of the word problem. So absolutely feel free to make a lot of notes on your homework on these kind of things. Now let's go for the direction of AX and AY. Let's think about AY. Which way does AY have to go? Got to go up. Because we're looking for equilibrium. We're looking for the sum of the forces in the Y equals 0. So this has to go up because this is coming down. This has no effect in the Y. This is going down. So that's definitely going to. What about AX? Equilibrium. We got to have equilibrium. It's got to go to the right. If BX is going left, AX is going right. So I always sketch in the reactions without the arrowheads, get them all in, and then I start to think about, like, can I figure this out? Sometimes you can't. Sometimes you won't know which way they go, and you'll just make an assumption. But they need to have directions. Questions?
It's always like the center.
Always at the geometric center. Yep,
No exception.
no exceptions. Yeah, it's not always easy to find the geometric center, but for a ladder, it's pretty simple. Yeah. But like if you were gonna put a human on the ladder, you would put the weight of me through my geometric center and acting straight down. Gravity always acts straight down. Thank goodness, or we'd be like flying sideways or flying up, right? All right. Any other questions? If they don't give you the weight, we don't include it. We don't want to make unknowns, okay? Like on the next problem, it says, for the structure shown, draw a free body diagram for both the beam ABC and the link BD. The members are weightless. They want to always tell you that. If you're not given a weight, don't include it. All right, so they want 2 free body diagrams, 1 for each member. So you draw them separately. Like that. I draw them in position, but apart, right? So the problem gave us this thing down here, right? So I tried to keep this in position, just drop it down. Label everything. So there's 2 point Bs, one on ABC and one on BD. They're the same point. I have just taken it apart. Right? We would include all the dimensions. They didn't give us any. We would include the angle 45. There's a pin at C, a pin at B, a pin at D. A lot of pins. There's some external forces, so we need those on there. P1, they labeled it, and P2. Again, if there was dimensions, we would want them on. All right. How many reactions does a pin get? I'll be saying that a lot. 2, an X and a Y, right? So each one of these gets a X and a Y. And it doesn't matter where you draw them. This one could be drawn here. This one could be drawn over here. This one could be drawn up. That doesn't matter. Right? And then B has a pin. And D has a pin. Any other pins? Did I miss any? So now I'm going to go through labeling. BY, BX, BX, BY, CX, CY, DX, DY. It's busy. Make your drawings big and separate them. Like this is really kind of too close. It's getting kind of busy right there. Everyone see all the pins? So when 2 things are connected, they're connected with what we call a free pin. It's like a bolted connection. Okay. And it can even be like 6 bolts at that connection. But we still call it a free pinned connection, meaning that it's free to rotate. Those bolts don't hold a lot in rotation. They're just holding things together in shear. So we call them pins. All right, now we just do our best to try and figure out directions. And you look at them one at a time. So, wow, I got a drawing on the back. So really you just kind of erase this one out of your mind and just look at the horizontal one and go, okay, can I tell which way the forces are going in the X? These 2, right? These are the only 2 in the X. We don't know anything about either one of them. So no, I have no idea which way they're going. So in that case, you just choose one. And then you make the other one balance it out. Because we know the forces in the X have to equal 0. Okay, same with the Y. I'm gonna look at this and go, okay, there's some coming down, so maybe BY goes up. But CY might go up to hold it in equilibrium, but if this is really big, CY could go down. There's too many unknowns. If you have two unknowns, there's no way to tell which way it goes. So again, you're just guessing. I'm gonna put it up. Guess at the directions. Assume a direction. When we do the math and we get negative numbers, that means your direction is wrong. We have to flip it over. Okay. So it will correct us. It's important that you guess though, because you're going to put the other piece in equilibrium. So when this pin comes together with this pin, that pin itself has to equal 0. Everything has to fight each other. So that means if BY goes up here, BY goes down here. If BX goes left here, BX goes right here. So when that pin comes together, it's in equilibrium. So the sum of the forces have to be equal to 0 for the system and for every piece of the system. Does that make sense? This structure is in equilibrium. So the sum of the forces of this structure is equal to 0. So that means this brick right here, if I was to pull it out and do a free body diagram of it, the forces coming down on that brick equal the forces going up on that brick, the forces going to the right equal the forces to the left, and every little grain of the brick also is in equilibrium. So everything. All right, so now that I assume that, which way does dy have to go? Yeah, because now I just look at that bottom piece by itself. Dy would have to go up, and dx to the left. The tricky part is when you then solve for this and bx becomes negative, that means bad direction. You got to flip it over. So that means you'd have to go up and flip that over. So it's kind of contagious, right? And it'll travel through the structure. When these structures get more complicated, yeah, you really got to watch it. So good. Are you getting it? Kind of understanding that? Everything's got to equal 0. So we got to have all those directions countering each other. When we know them. I mean, we don't know them. Here. Free body diagram. All right, 12. Was 9, 10, 11. 12, point B. Yeah. So this says calculate. Oh, this is actually a calculation problem. Did I give you this? Did anybody work this? It's quiet. It's like dead quiet, man. It's scary quiet. All right, it says calculate the force in cable AB and the angle theta for the support system shown. So we got to draw a free body diagram. I already gave it away. Where are you gonna, how are you gonna draw the free body diagram? You draw it at point B, right? Point B's got to be in equilibrium. Okay. So drawing a free body diagram at point B. What's that look like? What do we know about point B? £100, right? And then what about the weight down? That goes in. 200 pounds. Then we have a wire or a cable. So how many do those get? I get one. One reaction. We're taking the wire out, we're putting a vector in, a force. And it always works in tension. So it was pulling on this thing. Point B. There's an unknown angle here, theta. We know anything else? We need to label this somehow. A, B is what I'll call it. That's pretty common because the upper point was A, the lower point is B. We call it force AB. So they want to know what's the force in that AB and what's the angle. Right? So this is an actual equilibrium problem where we have to find those unknowns. So the only thing unknown is AB. But we know that if I add up all the forces in the X, it's got to equal 0. Right? And if we add up all the forces in the Y, it's got to equal 0. So let's think about this. And moments too. Are there any moments in this problem? Is there any rotational effect? What do we know about concurrent force systems and moments? There's no rotation. You have to have distances to get rotation, right? So the 100 pounds does not create rotation about point B. The 200 pounds does not create rotation about point B, goes right through it. And AB does not create rotation. So this is unnecessary in a concurrent system. We won't use it. It's all about these forces in the X and forces in the Y. So yeah.
I was gonna say, so would we find the resultant of the 200?
We don't need to, not asking for the resultant,
Okay.
right? And we know what the resultant is. 0. Equilibrium says there is no resultant. I'm glad you said that though, because that's what we just did for 3-4 weeks was resultants. They're gone. We don't do them anymore. Now we want to know what the force in AB is. How many forces are in the X? 2. What are they? Tell me. The 100 going to the right. And the ABX, right? The X component ABX. And it's got to be going left if that's going to the right.
-1.
Yeah, there's only 2. They got to be equal and opposite. So this thing is 100. Heading in the negative direction. Has to be. Right? Because we got to make this true. Tell me about the Y. You got 200 coming down, so that ABY, it's got to be how much? 200. Got to be. So now you know both components of AB. Just by observation, we didn't even use a formula for that. We just looked at it and said, hey, there's only 2 forces in the X. Those got to be equal. There's only 2 forces in the Y. Those got to be equal. And now we know the components of AB. How can I get AB? Pythagorean theorem. Yep. So AB equals the square root of 200 squared plus 100 squared. I need a little calculator action this morning. 223? Anybody else get that number?
Yeah.
223.61 pounds. So that's its magnitude. All right, and how would we get that angle? Yeah, we know the triangle, and these are opposite interior angles right here and here, correct? Yeah, so this is theta also. So it looks like it's going to be tangent theta equals opposite. That's the 200 over 100. Theta equals. $63.44. It's good. Our first equilibrium problem. Love it. This is really magic for the folks that don't know how to do it. Like when you go to work and you're asked to do these kind of problems, they'll be like, "How the hell did you figure that out?" Because this is the kind of stuff that I did a lot when I was with Keelan. Like they did a lot of lifting, a lot of cable work, and they were always like, "Hey, we only have cable rated to 2,000 pounds. Is it going to be okay for this lift?" Like, you know, I have to run some numbers on that, figure it out. I mean, that's what you just did is you figured out this wire has a load of 223 on it, right? So if they're asking like, hey, all we have is rope rated at 100 pounds, and then you crunch this, it's like, no, nope, that's not gonna work. Yeah.
Measure that,
Huh?
like in a real life work situation, would you measure that stuff, or would they give you?
For the rating on the rope?
Like a problem that you would have on work.
You don't measure it? Well, you mean to get the information?
Yeah.
Yeah, absolutely, yeah. Yeah, you'd have to know the pick height, the span of the pick, all that information. So you could potentially go out and measure it. Most of the lifting systems that they had at Kiewit were manufactured. So you could just look up the lifting specs on it, like how wide, how long they were. You had the lengths of both pick points, right? And then how far above it we're gonna be, so you can build all the triangles. And I mean, there was occasions where I would go weigh stuff because we just didn't know how much it weighed. So we'd take a truck and run it over to the scales, and I'd get a front axle weight and a rear axle weight. So I'd have a baseline to, so I knew something. But yeah, absolutely. All right, let's do another one. 13. Oh, 13. Trying to get myself some paper to work on. Zoom tight. It's like something going around, you know. You gotta be eating right, sleeping right, all those good things. Not working too hard. All right, 13 was another one, another equilibrium problem. I was pushing you forward, I guess. Calculate the horizontal force that should be applied. I bet you can do this now, though. Right? You just got to start with the free body diagram, which I started. What am I missing on the free body diagram? For number 13. It looks like that. I'm doing the free body diagram with this. I have the weight in. I have the force. The cable. Missing the cable. AB at 30 degrees from vertical. So let me get the cable in. And I'm actually drawing it right through the center point. AB. And it is 30 degrees from vertical. So 30 degrees there. This is a little trickier than the last one because F is unknown and AB is unknown. We have two unknowns. But we have two equations. We have some forces in the X and we have some forces in the Y. So if you have two equations and you have two unknowns, it's solvable. That's kind of your rule. If you have more unknowns than you have equations, you're into like a very difficult problem that we can't solve at this level. It's called a multivariable problem. So we always look at the number of unknowns and then we look at our equations that are available, and if they match or I have more equations than unknowns, I'm good to go. So if two equations, I don't have the moments, why not? Because there's no moments. It's a concurrent problem. All the forces intersect at one spot. What spot is that? B? At B. Okay. So we start with concurrent problems and then we're going to move to non-concurrent problems. So we'll be doing both kind of at the same time. But no moments, so we don't get that equation. But based on what we did on the last problem, what can you tell me? Yeah, looking at the Y forces, how many are there? Two. And they have to be equal and opposite. They've got to be equal and opposite. So that means that this component of AB, Y equals 100 pounds. Hopefully you see that. That's what we need to recognize. If I look at the X, how many unknown are in the X? How many forces are in the X? Two. What are they? F and ABX. ABX is going to go this way. But it's unknown. Because F is unknown, we don't know either one of them. Okay? But we do know the angle of AB. It's at 30 degrees. So that means that this is 30 degrees right here, right? Interior opposite angles, 30 and 30. So I know this is 100. I don't know AB, but I know the angle. We should be able to solve for it, right? It's a triangle. So if I pull ABX out, ABX, which is 100, oh, ABY, sorry, and ABX. Let's see, I should put somewhere else. And I know it's 30 degrees here. How can I find AB? Yeah, so you can use, tangent would use opposite. We want to use adjacent, don't we? Adjacent to the 30? Opposite over, oh, you're looking for this then. ABX, yeah, you can do that. You got to solve the whole triangle anyway. So yeah, we could go tangent 30 equals ABX over 100. Everyone see what I did? I just pulled AB out of the system and isolated it. And then drew the components, because we've done components a bunch. And then just applied some trig and going to try and solve it, right? I'm going to try and solve for ABX, because if I know ABX, what else do I know? F, because there's only two in the X, right? So I'm going to solve this problem by just this triangle right here. So what's ABX equal? Under tangent 30. 57, 7, 3, 5. So then what's AB equal? Pythagorean theorem, right? So AB is going to equal the square root of 100 squared plus 57.735 squared. Oh man, I just goofed up. Dang it. Oh, got it. $115.47. Ah. And what's F equal? Yeah, 57.735. There's only two forces in the X. There is this one and this X component, which we found right here. 57.735. So F equals ABX. Those two have to be equal. And opposite. They got to be oppositely directed. And they are. ABX is going right, F is going to the left, holding this thing out there. It's a game of seeing forces in one direction. You have to be able to spot the forces in the X, whether they're components or actual forces in the X. Okay, so you have to be able to visualize those components. And then when you see it, take a force, pull it out, and draw its triangle. And you'll be able to solve for stuff. Maybe not everything. This is a simpler problem where we could solve for everything. Sometimes you can just get this Y and then you got to move on to something else, right? So you just get pieces sometimes. This one we were able to solve it all. No moments. It's a concurrent system. So even though this looks like it's a distance away, its line of action goes right through the point. Okay, so cable problems, lifting problems, dangling ball problem, I don't know what the heck that is. They're all concurrent, right? Floating in space. Question? Does that help? Yeah.
So as long as the line of action goes through the middle.
Yeah. That's right. And it can get really tricky. Like, I could do this, or the world could do this, or whatever. It's gonna look like a, concurrent problem or non-concurrent problem. But if you're given those two, right, they actually intersect, don't they? So you could work it like a concurrent problem by just taking their lines of actions and putting them together.
So even if they intersect, then
Yeah. If you add one more though, and its line of action is here, never are those three going to intersect. Moments. That's when we got to use our moments. It's our third tool. Okay.
So that line wouldn't continue forever.
Now, well, this continues forever, and this one continues forever, but these two are parallel.
they all have to.
They all have to intersect for them to be concurrent. And parallel lines do intersect at infinity, but that's way beyond us. Like, no, we're not doing that shit. We're gonna use moments to solve the problem. It's way easier. So, yeah. So you do look for concurrency. If you see it, go for it. If you don't see it, then just do moments. And if your moments are coming up with 0, 0, 0, then that should trigger, oh, this thing must be concurrent somehow. So,
You said they go, wait, parallel lines?
intersect at infinity.
Is it because like, as you like zoom
Ah,
out? they
dude,
get
that's,
closer and
it's
closer?
beyond me. I don't know. Ask your mathematician.
Okay,
Ask your math instructor. Yeah, it's like a relativity thing, I think. I don't know. All right, let's do one. We're gonna do a non-concurrent now. It's number 25. So I'll give you some time to draw it out. This is definitely non-concurrent. Those three forces are not going to intersect at one spot. But now we have the tools. There's really no new formulas. It's the formulas we've used all along. But it's a new process. You can just go straight to the free body diagram if you want. You don't have to draw the pin and the roller. Got it? All right, how many does a roller get? Roller. 1. Always perpendicular to the ground removed and the roller and the contact. So roller gets 1, by. How many does a pin get? 2. So your first step on these problems is to put in these reactions, AY and AX, label them, and try to figure out their directions. Which way do you think AY goes? Oh, I already put BY up on you. But everything's coming down, right? 6K, 7K, 8K, all coming down. BY, AY are gonna have to go up. What about AX? Don't really know, but we know what its value is, don't we? Because we know if the sum of the forces are equal to 0 in the X, and there's only one force, what's it got to be equal to? 0. So you want to identify those right away so you don't spend time spinning your wheels trying to figure out what AX is. AX is 0, it's gone. If there was a force out here at an angle, then AX is not 0. AX has got to carry that X force. But there isn't, so AX is 0. All right. So now, here's the hot tip. If you don't know what to do on these problems, apply the equations. Just apply, just do it. Just get to it, right? So we did this one. Right? Sum all the forces in the X. There's only one, it's AX, and it's equal to 0. Okay, so the next equation says sum the forces in the Y. What are all the forces in the Y? So positive or negative on BY? Positive's going up. That's super important. So if you didn't know the direction, you assumed it. You have to assume it, and then you got to put the sign in the formula. Okay, we assumed it's going up, positive BY. What about AY? Positive AY. What other forces are there in the Y? We need all of them. Every force. Minus 6K. Right? What else? Minus 7K. Minus 8K. When you're summing forces, you're just looking at whether they go up or down, right or left, right? And when you're doing Y's, you're just looking at up and down. So you're isolating the translational Y effect of the system. We already isolated the translational X effect. So we do X, we do Y, and then we're going to do moment. This has got to be set equal to what? 0. There's the formula. How many unknowns? 2. One equation, 2 unknowns, you cannot solve it. Okay? But you can write it. And you have to write it. You got to okay, if I don't know what to do, apply the formulas and write them out. Okay? The next one is sum a moment. We got to pick a spot though. When we do moments, they're about a very specific spot, and it's up to us. At this point, no one's going to tell you, right? Well, where do I sum my moment? Anywhere, doesn't matter. The moment at any point has to be equal to 0. Just like this building, if I sum the moments right here of all these forces, which would be impossible, but let's just say we could do it, right? It's going to be equal to 0 because that brick is not rotating. It's sitting there. But it has rotational effect on it. Okay. So where do you want to sum the moment? A. A is a great spot because any force going through A, we don't include it because it doesn't create a moment if it goes through the point, right? So if I do it at A, what drops out? AY and AX, but AX was equal to 0 anyway, so. And any other force that goes through A would drop out of this equation. So you want to pick the spot where there's the most forces, right? We could have picked B, but don't pick out here because then these two create moment and they'll both be in the equation and they'll be unknown. So you want to pick a spot that eliminates unknowns. AY will be eliminated from this equation. So we're going to do moment at A. You got to include that so I know where you're doing your moment. We all can do it in a different spot. It doesn't. So I got to know, where'd you do your moment? Especially if you're talking to other people, where'd you do your moment? I did it at B. Oh, I did mine at A. So our numbers are going to be different. We should have the same answer, but our numbers are going to be different. All right. Now this is a skill we have. What are the moments about A? And we need all of them. Force times distance. 6K times 2. Rotation. Clockwise. Negative, correct? You're good with that one? What else? Moment at A.
Listen,
7K times 6. Rotation. Negative. I work it left to right so I don't miss a force. So I went 6K, 7K, now I'm gonna do BY. Absolutely need your unknowns in the formula, or you won't have anything to solve for. BY, what kind of BY times what? Distance. 11. Rotation. Positive. Clockwise. Counterclockwise, sorry. Counterclockwise, positive. Are we done? 8K times 14. Rotation. Negative. Can't miss a rotation. Got to really be careful with your rotations. I almost always draw the rotation symbol to remind myself which way it's rotating. And the whole thing has to be set equal to 0. That's equilibrium. All the moments got to sum up to 0. How many unknowns? 1. That means you can solve for something. Right? That's what we're looking for, is an unknown of 1 in the formula. Now it's just pretty simple algebra to get BY. Let's talk our way through it. How do we get BY? Yeah, we isolate it. So I just leave it there. And then what do we do with all the rest of the statements? They all move to the other side and their sign changes. So this becomes positive, it moves over. This becomes positive, it moves over. This becomes positive, it moves over. And then they're just numbers. And then to get rid of the 11, we divide it through algebra. All right. Do it. Anybody else get that? That's good because I wrote it in pen. I had to scribble. Good, we getting that number? Yeah. Now I know B now. I know BY. How could I get AY? Yeah, you have your other formula. So you didn't write that other formula for no reason. You can now just take BY, plug it into here, and get AY. So it would be 15.09 plus AY minus 6K minus 7K minus 8K equals 0. That formula, we just plug it in. And solve for AY. $5.91. Excellent. Now we know them all. We know BY 15.09, AY 5.91, AX is 0. There's no way by just looking at it we can tell how much load is here. We know it's a pretty big load because it's got 8 coming down and 7 coming down on either side of it. So a big portion of the 8 is carried here, a portion of the 7 is carried here, and a portion of the 6 is carried here. A little bit of the 6, maybe half of the 7, because it's a little more than half of the 7 is carried here. All the 8 is carried here. So it makes sense that BY is big. Right? So you want to think about this logically too, because you can kind of check your numbers that way. There's no way you'd come up with a number without doing the math. But you can estimate like, oh, this is going to be pretty big. It's going to be 15-ish, right? And then this one's going to be less because 8's a long ways from it. 7's a long ways from it. 6 is close. So that's kind of how you can logically think through vertical problems. More complicated problems you can't. You just got to go for it. It's good. Good so far? All right, let's just play with this a little bit. If I made the assumption that BY went down, right? Let's say I just didn't know and I guessed and said BY goes down. What's a change in this equation? That would go negative. Yep. And what's a change in this equation? Goes negative. Rotation would end up to be the other direction, right? It would be negative. So then when you solve it, it's going to go negative. You're going to get the same number. The number is good. But if you come up with a negative, the negative sign, when you run any of these equations and you come up with a negative, that means whatever you guessed at is incorrect. BY is the wrong direction. That's what that negative is telling you. It's not telling you BY is in the negative direction. It's telling you, you assume the wrong direction. Go switch it. Okay? Because BY is not in the negative, it's positive. So this is just telling you, hey, it's not pointing down. It's pointing up. So as soon as you get a negative, you go switch it, and then you switch the sign, you switch the sign, and you switch the sign. Yeah. Yeah, if you come up with a solution of BY being negative, you chose the wrong direction. Go switch it immediately. Don't continue on, right? Because you could use BY in a future formula. So you got to switch it right away. That'll straighten that sign out, and then you go back to work. So you won't get that for a while. You should be able to assume directions pretty easily on these simpler problems. But on the more difficult problems, you literally don't know. Like when we do trusses, there are so many unknowns that it's like, oh, I have no idea. Just start guessing, and then if you come up with a negative, you're like, oh, that was the wrong direction. Go switch it. All right, cool. Questions? That was a lot. You have a really kind of a simple one, kind of like this on the quiz. So I want to make sure you kind of get it a little bit. First, you have a free body diagram. That one's easy. And then you're going to have a simple find the force in a cable thing, right? But you're going to have to use these. We do one more. One more practice one. Let's see. I'll just make it up. We'll put a pin here. And we'll put a force in the middle here. Going down at 100 newtons at 4 meters. And then we'll put a roller here. That'll be 6 meters. And then we'll put one more force. 75 newtons at 2 meters. This is A, this is B. And we want to know what's pin A feel and what's roller B feel. Find the reactions. These are called reactions. Not resultants, not to be confused with resultants. All right. I'll let you go first, grind on it. So the system is free body diagram. Some forces in the X, some forces in the Y, and some a moment if you need to. Is this a concurrent force system or non-concurrent? Definitely non-concurrent. You're gonna have to do a moment. Free body diagram first. Then just apply the equations. Okay, don't look up if you don't want to see the solution. If you get stuck, look up. Good? It's not too, like, if you just follow the procedure, that procedure will hold up. You're gonna get to where you like see shortcuts. Like, right away, I can look at the problem and say, oh, there's two unknowns in the y. That formula is gonna do me no good. So I'd go right away to a moment. First thing I'd do, yeah.
The 75.
Huh?
The 75.
Where? Here? Did I screw up? Yeah, you gotta take the 2 away. So it's 8 up here. You see it? Great.
Yes.
Yeah. Easy to do, super easy to do. It's good. First equilibrium problems. This is good stuff, man. This is how we solve the rest of the term. This is all equilibrium. We're just on different stuff. We're gonna do trusses, we're gonna do frames, we're gonna do friction. It's equilibrium. All of it, all the way through. You're gonna get so sick of some forces in the X, some forces in the Y, some of moments. But you're gonna get so good at it too. Questions? You do. Give you, not a pile, but I gave you some. We can look at it. 15, 20, and 21. 15, 20, and 21. So I think they are, 15 is kind of like a concurrent problem. 20 is a non-concurrent. And 21 is non-concurrent, so. Pretty much like these though. If you see a distribution, what are you gonna do with it? What if you get a distributed force here? Concentrate it. Calculate the area, concentrate it, go to work like it's a concentration. All right. Because one of them has that, right? 21 looks like that. So what do you do with that distribution? What do you do with the 2 kips? 2 times 16, right? 32 through the geometric center. How about the 1 kip? 1 times 26, 26 kips through the geometric center. Now go to work. Okay? Anytime you see a distribution, concentrating. We'll keep doke. Break time if you need it. If you don't want it, you just want to grind out the quiz. It's right here. You can come get it when you're ready. When you're done with the quiz, you're done for the week. Unless you have a class after this, I guess. Or work. Or work. Well, we're never done with that. Or family, or friends, right? We don't want to be done with that. Or dogs and cats and guinea pigs, snakes. Anyone have a different pet than that? Dogs, cat, guinea pigs, snakes?
Yeah, I guess.
You got a hamster?
Yeah.
Does he have a hamster wheel?
No.
If I had a hamster, I'd have to have a hamster wheel.
Think about getting.
I want a hamster wheel for myself. Wouldn't that be, that'd be cool? Have a hamster wheel for a human in your house? And go for a run, try and crawl up that thing? Love it.